So for this talk, we'll be interested in safety verification of programs, in automatic safety verification. And the ideal situation would be if we would have an automated tool that takes as an input a program P and a safety property phi, and decides if this program satisfies the safety property. And ideally, it would either give us as an output a counterexample or a proof. Now, of course, in a general setting, this problem is unknown, so is undecidable, so we might also get an unknown as a result. A classic way to approach this problem is using inductive invariants. And in this setting, the automated tool gets, in addition to the program P and the safety property, an inductive invariant written by the programmer, say for all the loops in the program, and decides if the invariant provided by the programmer is inductive or not. Now, in case the program manipulates infinite state and the invariant has, say, quantifier alternations, then even checking the inductiveness of an invariant can be undecidable, so it can also return unknown. A more automated approach to safety verification based on inductive invariants is to actually infer the inductive invariants. Many times, the programmers don't like to write these inductive invariants by hand, and then we would like to have an automated tool that gets a program and a safety property and determines if there is an inductive invariant in some language of formulas for this program. And for this talk, we'll be interested in the decidability of this problem, which is parameterized by the language that we allow for inductive invariants. So I will first outline our main contributions. So we've investigated the decidability of this problem. And we, first of all, have some undecidability results. So for arbitrary systems, inferring a universal invariant, so invariants with only universal quantifiers, is undecidable. And also, if we focus on programs manipulating singly linked lists, then inferring alternation-free invariants, which is a slightly more extended class, is undecidable. And in both of these cases, the undecidability of invariant inference remains even when checking an inductive invariant is decidable. So checking if an invariant is inductive is decidable, but inferring an invariant is not decidable. We surprisingly have some decidability results. So for linked list programs, if we restrict ourselves only to universal inductive invariants, then it actually is decidable to infer an inductive invariant. And we can have some extensions of these results, and I'll show you some of them, for example, for network routing settings. So to set the stage a bit more formally for the rest of the talk, we are modeling infinite state systems using first-order logic. And this gives us the advantage that it has support from a lot of existing tools that are based on logic, on first-order logic. And a state of our system is a finite first-order structure over some vocabulary. And the initial states and the bad states of the system are described by first-order formulas. And the program is described by a transition relation, which is a two-vocabulary formula. I'll give you a short example of that. So here is a program iterating a linked list, and it's searching for an element of the list that satisfies the predicate P. And we would like to assert that when the loop finishes, either we found an element that satisfies P, or all the elements that are reachable from the head of the list do not satisfy P. So we can translate this into logic, and we get these three formulas for the initial state, the transition relation, which exactly captures the loop condition and the loop body, and the bad states that specify our safety property are exactly those states in which we exited the loop and the assertion is violated. To achieve this, to verify that such a program is safe, we could find a formula that is an inductive invariant. And let me say formally what exactly it should be, this formula. So it should satisfy these three conditions. It should be true in all the initial states. It should imply that you're not in a bad state. And it should be closed under the transition relation. And if a formula satisfies these three states, then we know that it over-approximates all the reachable states of the system. Now, all of these properties can be tested using satisfiability tests in logic. And since we are interested in decidability, our first step would be to restrict our logic to a logic for which these satisfiability tests are decidable. So the logic that we'll be working with is effectively propositional logic. it's first-order formulas without function symbols, and where the quantifier prefix is just exists for all. And for this logic, satisfiability is decidable, and there is also support from existing tools for deciding this logic. So how can we use this logic for verification? We would like the satisfiability of all these three formulas to be decidable. So this is easily guaranteed if the transition relation, the initial states, and the bad states are all satisfied by exist for all formulas. And for the invariant, we have a stronger requirement. It has to be alternation-free. So by alternation-free, I mean a formula that is a Boolean combination of existential and universal formulas. And the reason for this, that we need a stronger requirement from the invariant, is that it appears both positively and negatively in the consecution test. Now, I would like to point out that these restrictions are not real restrictions, because any Turing machine can be expressed using such a transition relation. But the restriction to alternation-free invariants is indeed a true restriction. But nevertheless, these kinds of invariants, this kind of modeling, and this kind of invariants are useful for many systems, such as linked lists, network routing settings, distributed protocols, and others. So based on this logic, we can create the following automated verification, where the programmer provides a program and a safety property, and an alternation-free invariant. Then we generate these verification conditions, feed them to an automated SMT solver, and this automated SMT solver will never return unknown, because the problem that we are solving here is decidable. So now the natural question that we asked ourselves is, let's say we don't know the invariant, but we do restrict ourselves only to alternation-free invariants, and we'd like to decide whether there is an invariant, an alternation-free invariant, for a given program or not. So first of all, of course, this is different from general safety verification, because it could be the case that the program is safe, but it does not have an alternation-free invariant. And the question that we ask ourselves is this decidable? So our first result for this work is that we show that inferring alternation-free invariants is undecidable, even though checking them is decidable. So next, we ask ourselves, how can we get decidability? Because we would like to have things that are decidable. So a first idea might be to restrict the language of invariants. Instead of all alternation-free invariants, let's only restrict to universal inductive invariants. But it turns out that inferring those invariants is also undecidable. Another idea might be to restrict the set of systems we're considering, not everything that can be expressed using EPR, but only programs manipulating linked lists. And inferring alternation-free invariants for these programs is also undecidable. So the last thing that we can do is we can combine both of these and talk about inferring universal inductive invariants for programs that manipulate linked lists. And it turns out that this is actually decidable. So now I'm going to spend some time explaining to you how we were able to prove this result. So after we have this, so our goal is to get to this picture where we have a program and a safety property, and we decide with no unknown in the middle if there is a universal inductive invariant for this program or not. And the first thing we ask ourselves is, in case there is no inductive invariant, what should we provide for the user? What would be a witness for the fact that there is no inductive invariant? And the answer for this is a notion that we call relaxed trace. So I will explain it now. We first have to recall the notion of a logical substructure, and we denote it by this less than symbol. So a logical substructure is obtained from some structure by removing some elements and dropping them also from the relations. And the key property relating substructure and universal formulas is that any substructure satisfies more universal formulas than any of its superstructures. With this notion, we define the concept of a relaxed trace. A relaxed trace is a sequence of states of the system, such that the first state is an initial state, and every transition is either according to the transition relation of the system or a transition to a substructure. And the key property of a relaxed trace is that if there is a universal inductive invariant, then any relaxed trace cannot reach a bad state. The reason for this is that the invariant holds in the initial state. It's preserved across the transition relation edges. It's also preserved under substructure because it is a universal formula. And therefore, if a universal inductive invariant exists, then no relaxed trace can reach bed. Conversely, if a relaxed trace that reaches bed exists, then it means there is no universal inductive invariant for the system. So this would be the picture now, that we either give a universal inductive invariant, or we provide the user with a relaxed trace. So this suggests a naive algorithm for deciding this problem. We can enumerate all universal sentences and check inductiveness. And we can, in parallel, enumerate all relaxed traces of the system and check if we find one that reaches bed. The problem with this is that it could be the case that none of the processes will terminate, because what if there is no universal inductive invariant and there is no relaxed trace that reaches bed? And the way to solve this problem, as it turns out, is that if the substructure relation is a well quasi-order, then this situation cannot happen, which means one of these processes must terminate. So I will spend a little time explaining the notion of a well quasi-order and how it's used for this decidability. So a set is well quasi-ordered if any infinite sequence contains I less than j, such that xi is smaller than xj with respect to the order. So an order that satisfies this property is a well quasi-ordering. And if the substructure relation is a well quasi-order, then it's possible to show that there is either a universal inductive invariant or a relaxed trace that reaches bed. So with this property, we get actually an algorithm, but it depends on the fact that the substructure relation is a well quasi-ordering. So if it is a well quasi-ordering, then inferring universal inductive invariance is decidable. So our next step is to show that the substructure relation is indeed a well quasi-order for programs manipulating linked lists. How much time do I have? 10 minutes. OK, great. OK. So linked lists, the structures that are created by programs manipulating linked lists are directed forests, as the one depicted here. And in a series of works by Itzhaki et al., they show that these can be modeled using effectively propositional logic. And what we show in this work that gives us the decidability result is that the substructure, when you use this encoding, is indeed a well quasi-ordering. The way we obtain this result is by using Kruskal's tree theorem, so Kruskal's tree theorem states that the tree homomorphic embedding is a well quasi-order for undirected trees. And the key insight here is to connect the substructure relation when you use this EPR encoding to homomorphic embedding in trees. And this finally gives us this result, that inferring universal inductive invariance is decidable for programs that manipulate linked lists, and the full proof of this appears in the paper. So the next thing that we now ask ourselves is, can we improve on this somehow? And a possible improvement would be to extend the class of programs for which we know that inferring universal invariance is decidable beyond linked lists. And I'll give you an example of an extension that we might be interested in, and that is network routing. So in a network, in many cases, it's composed of switches, and each switch has a routing table that determines for every possible destination of a packet what would be the next hop of this packet. This can be modeled by a global ternary relation that we call route that states for every destination, if a packet to this destination gets to this switch, what will be its next hop. Now, let us focus on one single destination. Let's say that the packet is destined to host 1. If we just project this relation onto just when the destination is 1, we get this binary relation, which we can draw as a graph. And this graph depicts how packets destined to 1 will be routed in the network. Similarly, we can do for any other destination. And the key insight here is that any such projection, the structure is exactly the same structure that we have for linked lists. So the idea here is to leverage the decidability result that we have for linked lists to this kind of situation where we have a relation whose projection whose projections are linked list-like. But still, for this general setting, even for this setting, inferring unrestricted universal invariants is undecidable. But we did manage to get some decidability for this. And the way we did this is to restrict the language of invariants further, not to include all universal formulas, but only to allow formulas that uniformly treat all projections of the relation and cannot create any correlation between different projections. So you see here an example of a formula that is allowed and the formula that is not allowed because it correlates projections over different destinations. And next, I'd like to show you how we prove that inferring invariants in this restricted language that is denoted here by L-proj is decidable. So the outline of the proof is that first we need to generalize the substructure relation to another pre-order that is parameterized by the language. We also need to generalize the notion of a relaxed trace to an L-relaxed trace parameterized by the language for invariants. And then we establish a well-quasi-order result which guarantees decidability. So for any language of formulas L, we can define this order relation that a structure is smaller than another structure if it satisfies more formulas from the language. So a smaller structure should satisfy more formulas. And if you consider the language of all universal formulas, this exactly corresponds to the substructure relation. Now, what is the meaning of this for this language of projections? So you can see here an example of a structure with a ternary relation, and here also another structure with a ternary relation. And we've depicted here the projections of these relations. So the projection onto destination 1 is depicted in red, and to destination 2 is depicted in green. Now, this structure is not a substructure of this structure, but it is smaller than this structure with respect to this language of projections. And the reason is that any formula that universally mentions all projections here, that universally mentions all projections and is satisfied by this structure, must also be satisfied by this structure. The reason for this is that the green projection here is the same as the green projection here, and the red projection here is also the same as the green projection here. So if the formula is satisfied by the green projection here, it is also satisfied by the red projection here. And with this generalized order relation, we can define a relaxed trace parameterized by the language. So very similarly to what we had before, the first state should be an initial state, and every transition is either according to the transition relation, or it goes to a state that satisfies more formulas from the restricted language. And just as before, an L-relaxed trace that reaches a bad state is a witness to the fact that there is no inductive invariant from the language L. And following a very similar proof to the one presented before, we can also show that if this order relation is a well quasi-ordering, then inferring invariants in this language is decidable. So now the last thing we have to do is to show that for this language of projections, this order relation is indeed a well quasi-order. So to prove that it is a well quasi-order, we have to show that in any infinite state of structures, there is some I less than j, such that the structure I satisfies more formulas in the language than structure j. And the way to do this is to transform these structures into sets, into finite sets of all of their projections. So here, every structure here is finite, so it has finitely many projections. And each of these projections, instead of the ternary relation, contains a binary relation. The next step is to define an order relation on these sets, such that a set is smaller than another set if every structure here is a substructure of some structure here. This is also known as Hoare order. And a key thing to note is that this order relation is exactly the substructure relation for which we know that linked lists are well quasi-ordered by this relation. And indeed, the structures that we have here are similar, are exactly the structures that we get for linked lists. And this lets us use Higman's lemma, which is a well-known result in well quasi-order theory, that gives us that if some set is well quasi-ordered, then also finite subsets of this set are well quasi-ordered by this order relation. So this order relation is, so these finite sets are in fact well quasi-ordered by this order. So from this we get that there is some I less than j, such that the ith set is smaller than the jth set. And if you now think a little bit about the meaning of these projections and our syntactic restriction on the formulas, that it can only mention all projections universally, then you see that if a set is smaller than another set with respect to this order, then the corresponding structure must satisfy more formulas from the language than the structure corresponding to the higher set. So I hope you think this is as beautiful as I find it. And this eventually gives us that this order is indeed a well quasi-order. And for this, and following the argument that we used before, the inferring invariance in this language of projections is decidable. OK, so let me wrap up. So our long-term vision, if you want, would be that we have an automated tool that gets from the program a safety property, and is parameterized by some restricted language, and it automatically infers invariants in this language, or it decides that no invariant exists, and in this case it gives a relaxed trace that demonstrates this. And in this work we've explored the decidability of this problem, and we've seen some cases where it is undecidable and some cases where it is decidable. So for linked lists we've seen that inferring alternation-free invariance is undecidable, and inferring universal invariance is decidable. We've seen that if we don't have this restriction to linked lists, inferring universal invariance is undecidable. But we can have other restrictions by further restricting the language that also maintain decidability. One that I've shown you is to relations that have nice projections, projections for which we have a well quasi-order result. Another extension that we have in the paper is that if we have some relation that doesn't have any nice properties, we can still allow it in the invariant as long as we bound the number of occurrences that it can appear in the inductive invariant. And another takeaway from this talk is that really the problem of inferring inductive invariants is different, of course, from the safety verification problem, but also from the invariant checking problem, because as I've mentioned, even for this case and for this case, which are undecidable to infer, checking invariance is decidable. So that's it. Thank you.
We have time for a couple of quick questions.
Hello. Usually when you have a termination proof using well quasi-orders, you can look a bit more carefully at it and get some upper bounds as well. I was wondering if you think that it's possible to do that for your proof.
So the question was about upper bounds for inferring inductive invariants. So I think we don't have any upper bounds at the moment.
I mean, there are some generic techniques for looking at proofs that, of termination using well quasi-orders that give you upper bounds. And I was wondering if you think those kind of techniques would work for the proof you have.
So I'm not sure that they would work, because even if we have, even if we have some bound on the, so the well quasi, even if we have some bound on the length of the largest sequence that does not contain such pair, it is not clear how we can translate it to a bound on, say, the length of the relaxed trace that we should look, or the size of the invariant that we should look. So it would be very interesting, but we haven't been able to obtain such a result.
So your results essentially say I enumerate all the counterexample traces and I enumerate all the candidate invariants, and when either of these processes is going to finish.
Yes.
But that's extreme. This is nice for just for the decidability because it's extremely brute force. Do Do you think there could be something like a counterexample-based approach in order to synthesize such invariants that maybe you would not be able to prove a complexity bound for, but at least that would be less brute force than what I've just said?
Okay. So indeed, the algorithm that so this algorithm is just a thought experiment. It's nothing you can do in practice. And there are indeed works that have practical heuristics for doing this. In particular, last year's CAV presented, last year or the year before, presented a PDR-like algorithm for inferring universal invariants, which is along the lines of what you suggested. And definitely, this is something that we would very much like to have, something that works in practice and not just this piece of theoretical algorithm.
Let's thank the speaker again.
Okay.